thank you very much. So today I talk about this fluctuation versus evolution. And so this is the menu. And so fluctuation versus evolution, fluctuation by genetic change and epigenetic change, and evolution of robustness, and characterization of plasticity, and restoration of plasticity. In some sense, theoretically speaking, it's a story about selection of dynamical systems by dynamical systems for dynamical systems. So it's an anniversary in the same thing. So the first, so we have some feeling that some species are faster to evolve. So it's a kind of very naive, ambiguous question. So here I like to do this type of question to make a more quantitative science by idealizing the issue. And so first, these days, there are lots of measurement of phenotypic fluctuation. For example, this is a protein concentration measured by fluorescence. So for same gene, isogenic, same gene bacteria. So even if they have the same gene, still there is a quite large change in protein concentration or phenotype. So the question is that, so does this kind of fluctuation may be related to evolution or not? So that's this question. And so the motivation of this first is this relevance of this fluctuation to evolution or positive role of noise. And the second motivation here is evolution of robustness. And robustness is a kind of insensitivity of fitness or phenotype to systems change. So there are many ways of systems change, however. So one is due to environmental change, the other is some kind of due to noise during some kind of developmental process. And of course, in the evolution, this is also against some change in the system by mutation. So the question here is that, is there some relationship among these robustness, or does the evolution increase this robustness or not, or something like that? And here, the motivation of this first and second are bit related. Because in some sense, so insensitivity of phenotype means that the system does not change so much. So if it fluctuates a lot, it changes more. So it has a lower robustness. So very quantitatively speaking, so we can measure this robustness in terms of fluctuation. And so we try to see the evolution of robustness in terms of phenotypic fluctuation. So the first experiment we did, this is the beginning of this type of study, is 6 years ago. So it's a selection experiment of bacteria. So in this bacteria, there is fluorescent protein. And so initially, this fluorescence was not so good, so not so high. And what we did is that to make some mutation to this bacteria, and so there are some, so bacteria has a higher fluorescence and some are lower fluorescence, and select a higher fluorescence. But as I said already, even for the same gene bacteria, there is large fluctuation. So this is for the same gene bacteria, so in the beginning. And so we make some mutants, and this is the highest. But again, for this, there is large fluctuation. So the question here is this fluctuation and this evolution speed. So evolution speed is the increase of the P position. Is that related or not? And it looks like as the evolution progresses, this evolutionary step, this increase of evolution, this fluorescence decreased, and also fluctuation decreased. So it seems that there is some kind of correlation between fluctuation of isogenic bacteria between this fluctuation speed. And actually, so I come from statistical physics, and this reminded me a little bit of fluctuation response relationship in physics. And they say that in thermal equilibrium, so there is some kind of response ratio, so put some force to the system, and there is response. So, for example, some change of current or something like that. So this change of x divided by force. But even without putting this force, there is already some fluctuation. So we can measure this variance of this fluctuation. And what they say is that this variance and response ratio is proportional. So that started from Einstein's paper. And of course, this is true only in thermal equilibrium or near thermal equilibrium. But we can somehow generalize this type of argument by considering this distribution P of X. So X is, for example, phenotype. A is some kind of control parameter. And then by changing the control parameter, this distribution changes. And so by assuming some kind of Gaussian type distribution, if this variance is larger, so by changing the A, so this change is larger. So this response of the change of X by divided by delta A. So this is proportional to this original variance. So if this is larger, this step is larger, and smaller, this step is small. And so, yeah, I skipped these details, but anyway, starting from Gaussian distribution like form, and then, yeah, we can say something like that. But of course, this is some kind of, yeah, approximate theory. And first, we need to assume that this what we want to argue is that somehow this is represented by distribution of P of X parameterized by parameter A. So in some sense here, X is phenotype or fluorescence in this experiment, and A is gene. Yeah. So both are written by single scalar parameter. So that's a big assumption. And then also for this, so some linear coupling or some Gaussian form is somewhat assumed. So we need to check this experimentally. And so this is the experimental result for the previous experiment by bacteria. So this is variance of this fluctuation. And actually variance multiplied by mutation. And here is the evolution speed. So increase of the fluorescence per generation. So increase of the fluorescence per generation divided by mutation. So that is delta A. Is proportional to the variance. So instead of dividing by mutation rate, we put multiply here. So the result is this red sum. So it looks like somewhat, yeah, correct. And in contrast, we put just a very naive plot, just mutation rate versus evolution step. So this is a black one. So compared with this black one, red one is better. So in this sense, so maybe, yeah, fluctuation is somewhat correlated to evolution. And to check this argument, we did a little bit more on some other model study. But actually, I did not have time to go into this model. But anyway, that's some kind of reaction network model. And so gene determines the network structure. And then, so some resources are coming in, and this cell grows. And here, these X are several different proteins. And the concentration here. And so, what in this experiment we want to do is that prepare different type of mother cells with a different reaction network. And from each parent cell, mutant cells are generated, and by slightly changing the network structure. And then do this reaction dynamics and choose such cells with a higher fluorescence of some given protein. And then with this numerical experiment, this evolution speed and fluctuation, and for given course of evolution with given mutation rate, mu. So this looks like almost proportional. So it looks like okay. But this gives a new mystery. Actually, in population genetics, there is a famous theorem by Fisher. Is evolution speed is proportional to phenotypic fluctuation by genetic variation. So in this case, genes are different. And according to the gene difference, this phenotypic variant is different. So gene is distributed, and accordingly, phenotype is distributed. And this variance is proportional to evolution speed. And this is quite natural because this change by gene is heritable and transferred to the next. But in the previous study, what we did is that phenotypic fluctuation of this fluctuation itself is not heritable, because it's not encoded in gene. So, but in the previous segment, this and evolution speed seem to be, yeah, okay, so this is proportional to the evolution speed. So that means this VIP and VG seems to be proportional. So I use VIP here so to show that the same gene isogenic organisms phenotype variance. And actually, in population genetics, so there are some words VE and VG. And VG is that usually the variance due to genetic change. And VE is what they say environmental. But sometimes they say that this is something all others from a gene. So in that sense, we can include VIP here to VE. But anyway, mostly here VIP is due to some noise in the process. But anyway, we can include all of these. So it's basically some kind of terminology. So in the previous cell model, so this is model, we checked if this VIP and VG relationship. And for given evolutionary cause, this looks like proportion. You know, VIP is the process of the same gene bacteria, so it does not depend on the mutation rate so much. But on the other hand, VG is due to genetic change. So if the mutation rate is larger, so genetic variance is large, so VG increases with the mutation rate. So by increasing the mutation rate, it increases. And then it looks like there is some kind of maximum mutation rate around here. And beyond which evolution does not progress. And what occurs there is that, so here is the distribution of phenotype. And if you increase the mutation rate from here, here, then at least critical mutation rate, it looks like almost flat. So in some sense, then we cannot choose a good one. So if in this distribution, we can select, for example, a good one, but here we cannot select a good one. So this kind of, maybe we can say error catastrophe, occurs around here. So the question is why? And actually, we have not a clear answer yet, but this is a rather phenomenological argument. So assume that distribution of phenotype and genotype. So now we consider two variable distribution instead of a one variable distribution parameterized by another. So we have PXA two variable distribution. And then assume that through the evolutionary cause, this distribution keeps a single peakness over two variables. Maybe this is a rather natural assumption to have a robust evolutionary process. Then, by that, so there is some kind of condition for stability of two variable distribution. And then from that, we can derive some relationship. So for example, if we consider two variable Gaussian distribution, phenotype distribution X, and mutation, mu, and genotype distribution, and some coupling here. And then by rewriting this, we have for stability, we have this should be negative, and that gives some condition for the mutation rate. And from that, we can derive a relationship between VG and VIP. And if the mutation rate is small, we can rewrite this relationship as VG is roughly equal to mu divided mu max and mu max. At this point, VG and VIP are almost equal, and VIP. So if you put mu max here, VG is roughly VIP. And so this relationship is, so from this argument, it derived. And then if this is true, VG and VIP are proportional. And so in that sense, so okay, we derive this, and then error catastrophe around here, and this relationship. And so far, these are consistent with the experiments. But still, there are many Yeah, questions again. So first, existence of this distribution assumption, is this correct or not? And also this robust evolution assumption, is this correct or not? And also in the beginning, so VIP is better to be large in this, but it's the fluctuation for the same gene bacteria. So to have large VIP, you need some noise in the developmental process. So in some sense, this argument says that noise in gene expression dynamics or developmental process is necessary to have robust evolution. So the question is that if this argument is true or not. And then, so we put gene expression dynamics. Now we did some simulation of gene expression dynamics. So several genes are here, and these, so it's sensitive kind of protein concentration. And this, if this gene is on, so this is expressed and produce some other protein. And so, but these are usually mutually interacting. So it's constructed a kind of network. So if this affects class and if this gene is on and this gene is expressed, then it's a class. And if suppresses the other, it's negative. And if it's not related, so there is no connection. So we can write down some kind of connection dynamics of this gene expression level, xi, and mutually so activate or repress with this matrix jij with plus 1, minus 1, 0, according to activation, repression, or relationship, and put some noise here. And so in this model, so it's a dynamical systems model, and we have several, so in most simulations, 64 genes. And we put some output genes, for example, in this case here, 8. And these, so as a fitness, we assume that these 8 genes should be on. So if in this simulation, if 8 of xi, so here x1, x2, x3, x8 is positive, then it's fitness. And one of them is negative, it's minus 1. And 2 of them is negative, minus 2, or something like that. So what we did is that run this dynamics and select such cells with higher fitness. And again, we put some genetic algorithm to change that reaction, this gene expression network. So gene controls this network structure. And this expression level is a phenotype. And so, for example, in the simplest 2 cases, so starting from on-off genes. And then after dynamics, it goes to positive 1, so 2 of them are expressed. And so that's fitness. But if one of them goes to here, then this is minus 1, and if it goes here, minus 2. And so by doing this evolution experiment, so since this is not a difficult task, after a few hundred generations or something, it goes to this fittest state, that the fitness is 0. And so here, what we plot is, so that this is the top one. So actually, in this genetic algorithm, for example, I used 100 populations, 100 different networks. And so the top one means this top fitness, the network with the top fitness among these 100 populations. And this green one is the lowest. So this is the result for low noise case. So the top one goes to the high level, but there are some back mutants, and the average is not so high. But in the high noise case, in the same model, this evolution occurs like this. So top one and lowest one also goes to the highest level. So, and actually, so the distribution of the fitness, so if the noise is larger, then it's sharply distributed around the highest. And if the noise is smaller, then it has a tail to lower values. And so there is some transition at some noise level, and this average fitness goes down when the noise level is decreased. And then we checked this previous relationship between VIP and VG, so this is the variance of the same gene cells, and this is VG is some variance due to different gene network. And again, for given evolutionary cause, for given mutation But if the noise level is smaller, then this does not occur and it stays around here. And this line is VIP equals VG. So the previous argument seems to be again true here. Then the question is why this is so. And so after measuring some kind of basin structure of this dynamics, so that is from what initial conditions this goes to this high fitness state. And what we found is that in the network evolved in the low noise case, even for the top fitness case. So there's many, so by changing different initial conditions, it easily goes to a lower fitness state. So here, if you start from this given initial condition, it goes to the highest fitness state. So that's given, so this is selected. But if you change the initial condition, it goes to many different attracting states that has a lower fitness values. So the structure is something like that, so schematically speaking. So starting from other chocolate, those are different attractors with a lower fitness. But in the case of high fitness state, we found that many initial conditions go to this high fitness state. So the structure evolved like this. So in some sense, this is a kind of funnel type structure, so many initial conditions are so attractive to this high fitness state. And actually, in the case of high noise, so the dynamics try to make evolve so that some, so there are, so in this, actually, in this dynamics, the dynamics are rather complicated. So that there is many turning points in the orbit. And so starting from here and goal should be here, but there are many other ways to go out. So, but there are many such dangerous points in this gene expression dynamics. And then the system tries to evolve so that these dangerous points are not closer to the, it does not easily touch with these dangerous points. So this is a rough argument why this kind of evolution of robustness occurs only for high noise case. Okay, so in that sense, so we have seen evolution of robustness. So robustness is against noise or against parameter by mutation. And so this is so for the same gene network. So this is VIP is related to this robustness against noise. So the same one, but if VIP is smaller, means robustness is larger. And VG is against parameter change. This is because mutation to this. And so if VG is smaller, this robustness against mutation is larger. So what we have seen is that if noise is larger, this VIP and VG both decrease. That means both robustness increase. So noise is necessary for evolution of robustness. And this type of argument is a little bit similar to Waddington's genetic assimilation. Okay, so we have seen this robustness of evolution of robustness occurs. Then, what type of some characteristics of these robust dynamical systems have? And here, we have checked what happens to non-target genes. So target genes, I mean, is that among 64, 8 genes should be on. So that is related to fitness. But other 56 can be either on or off. So it doesn't matter. So it can change by mutation or something like that. But what we found is that after generation, many of Xi of this is either become fixed to positive or negative. So on or off. And some still change, plus or minus. But most of them so far. So some kind of this, so consolidation of other genes occur. And then, so we can check the evolution speed to each fixation for each gene. So now we plot the variance of each gene expression. Now the variance, it's not the variance of the fitness, but each variance of each gene, so VIP of each gene I. And then we can check the evolution speed for each gene expression. Now, if we plot this, it looks like, again, almost proportional. So this is different from the previous argument. It's for given snapshot, given generation, and taking many genes, and over genes, this proportionality between evolution speed and fluctuation seems to be true. Then that means probably we can see the positive correlation or proportionality between VIP and VG for each gene expression. So we have 64 genes, and for each gene expression, we can measure the fluctuation by genetic change and by noise. And so by noise VIP and by mutation VG. And then, so for example, for the high noise case, at given subgeneration, VIP and VG for many genes, over all genes. And so many are proportional. There are some that are deviating. And if the noise is smaller, then it loses a little bit robustness, and then some are proportional, but there are some other genes that are deviating from the proportionality. And if the noise is much smaller, below the threshold, then all are scattered. So anyway, when the evolution of robustness occurs, that there seems to approach appear this single unique slope. So in some sense, so as this robustness increases, you have this structure between VIP and VG of all genes. And then as the robustness decreases or some kind of plasticity increases or some possibility for higher dimension dynamical change, then there are some other genes appear. And if the noise is much smaller, then all become unstable. So that structure seems to be common here. And then the question is why this kind of proportional relationship occurs. And maybe so much time. Okay. So anyway, so here again I did maybe some kind of argument of this distribution function of PXA, but for all genes except. And again, some kind of stability condition, and then at some mutation rate, this stability is lost. And here, if we assume that at some mutation rate, many genes lose the stability at the same mutation rate, so kind of error some kind of percolates, and then so all the distribution becomes so flat for many genes at the same mutation rate. If we assume that, we can derive this kind of relationship over all genes. And here, we should note that this relationship is not necessarily true for any dynamical system. It's not true. It appears only after evolution. So here we did some experiment, numerical experiment, to increase some thickness. And after these evolutionary steps, this kind of proportionality appears. And we think that this kind of relationship is rather general, but maybe we can discuss later. And so anyway, in many cases, we assume that VIP and VG are proportional through evolutionary cause and also over genes at given generation. And experimentally, we are not completely sure. But here is an experiment by Drosophila about, this is about 10 years ago. And so they select these Drosophila for some trait, for example, like age or weight or something like that. And this is so variance of within the lines, so that means VIP. And here is among lines, this species. And it looks like has some kind of common proportionality over many traits. So this seems to be true. And actually, there is a recent experiment by this group, and it's more quantitative. They measured 4,000 genes of yeast. And in this case, so they measured something similar to VIP and VG here, not completely same, but and in this case, so there seems to be some correlation, but not so clear proportionality. And probably the reason for this difference is that in this case, they did selection experiment. But then, in this case, they did just measure this one type. So maybe that's the cause for difference. Okay, so, and now, far in these studies, in this directed evolution for given fitness condition, fluctuations decrease, and robustness increases, and evolution speed also decreases. So in some sense, after some generations, evolution slows down and fluctuation goes down. But of course, in nature, as I said in the beginning, there is large fluctuation, and evolution did not stop. So the question is how this evolution continues, or why large fluctuations exist in the present organisms. Also, there are some regained fluctuations. And in a recent experiment, we found some kind of appearance of mutants with large fluctuations. But I cannot go into details of this. And in the model, what I did is that I changed the environmental condition and see what happens. So, for example, so here, initially I said that 8 genes should be on. So, by some kind of according to some environmental change, here I assume that these genes should be on, but these genes should be off. So the fitness condition changed, switched. And see what happens. So by this switch, so initially the fitness is very low. But then after some generation, it increases. And here I put VIP and VG of the fitness. And so after the evolution, we start. So this is the beginning. And then both increase proportionally and then come back again. So in some sense, this proportionality law is somewhat true, not for decrease, but also for increase. And anyway, to adapt to new environment, both of them increase and adapt to new environment. And actually, if we measure for all genes, so all gene variants, then the distribution, so initially here, this proportionality line, but then some others appear, and this touches this instability line, and then new type of plasticity or new type of instability increases, and then produce a new wave of dynamics, and then starts to decrease, and finally proportionality appears. So in some sense, so this works as a measure for biological plasticity. If this goes here, it's smaller, and to have plasticity, maybe you need something like this. And finally, so we did some experiment, numerical experiment, by changing the environmental condition, so frequently. So this is switch the fitness per, for example, 20 generations between this and this, or 10 generations. And then, if the noise is very small, it again cannot adapt. Well, it cannot have a higher robustness, and the fitness is not good. But if the noise is too large again, previously it was okay to have robustness. But if the noise is large, then the fluctuation is so small, and they cannot adapt to the new environment. And so actually, this is the case of this green line. This blue line is the case of the highest noise, large noise. So it cannot adapt to this fitness. But in the middle, just near the critical point of this noise, so the fitness goes up and goes up again. So it can adapt quite rapidly and also robust. And so the average fitness plotted against noise level has some peak around this transition point, so near the critical point. And so, in some sense, near this, if we plot VIP versus VG, if the noise is large, then it stays there. But if the noise is small, again, this is too large. But if in the middle range, so it goes up and goes down like this, near this, yeah. So probably in the wild type, this type of structure appears because the environment is fluctuating and so on. Okay, to sum up, so we discussed about this biological relevance of phenotypic fluctuations, and fluctuation is proportional to evolution speed, and then we discussed proportionality between isogenic phenotypic fluctuation VIP and fluctuation by mutation VG, and is proportional first through the evolutionary course. And then we check this is true also over maybe genes. And then this issue is discussed in this relationship between robustness to mutation and robustness to developmental nodes. And finally, regain of fluctuation and evolvability is found in fluctuating environment. And in this case, optimal noise level to give criticality and that is relevant to adaptation. Okay, thank you.